Hello, my research topic is multiscale semantic understanding of remote sensing image captioning. I will introduce the following aspects, starting with the research background. Trying to describe the image below, it is easy for a human or even a child, but difficult for a machine because it only knows 1 and 0. So image captioning is let the machine understand an image and output a human-like description. There are 3 types of image captioning: natural image captioning, medical image captioning, and remote sensing image captioning. We will do research on remote sensing image captioning, meaning that the images are acquired through remote sensing technologies. Here is an example of remote sensing image. There are challenges for remote sensing images. First, remote sensing images taken by drones are area of use and usually cover extensive areas. So these images contain much information and may lack main targets. Like the pictures of plants below, it's hard to determine which is the main target. The second is the multi-scale problem. As shown in the images below, the leftmost section displays different sizes of airplanes within the same image. Moving from left to right, the aircraft scales exhibit variations across the different images. So we will design an encoder and decoder architecture to address the above 2 problems. In the encoder, we employ CNN backbones for filter extraction from remote sensing images. Next, we utilize 2 methods, namely spatial pyramid pooling and filter pyramid, to address the multi-scale challenging. The fusion technique is used to obtain the final filter representation. In the decoder, we introduce the transformer block. The self-attention mechanism is effective in capturing non-term dependencies and high-level features. And self-attention can also address the lack of main targets by governing the model's allocation of attention. Let me give more information about the 2 methods. The principle of SPP is to divide the input feature map into grids of different sizes. The small-sized grids capture fine-grained details. The large-sized grids capture more global information. Within each grid, the pooling operation is performed to obtain a fixed-length representation of that region. Finally, the features extracted at different sizes, along with the feature map from CNN, are fused using the concat operation. The principle of LP is to create a feature pyramid. Firstly, a top-down pathway is obtained by upsampling the feature maps at the topmost. Then, the lateral collections create a feature pyramid. Finally, the high level in the pyramid is upsampled and low level is downsampled to get a fixed size for future fusion. Remote sensing image captioning is a relatively new branch, and there are fewer datasets in this domain. There are 3 mainstream datasets, namely UCM captions, Sydney captions, and ISICD. All of them are open source and can be downloaded online. The image caption network requires assessment techniques to evaluate the quality of generated captions. We use 7 common evaluation metrics, namely Blue 1, 2, 4, Rusher, and Meteor, Cider. The higher the score of these metrics, the higher the quality of the captions. We have set some basic parameters when training the model. Next, we will perform several experiments, like the comparison experiment, ablation experiment, and comparison with some state-of-art methods. First, we compare the performance of the baseline SPP-based and FP-based models. The results in the table exhibit an improvement for the models based on the SPP and FP module compared to the baseline. Moreover, the FP-based model performs better than the SPP-based model. This may be because the feature pyramid effectively integrates both high-level and low-level information, and SPP only processes high-level features. And low-level features can also learn image details such as shapes and colors. Next, to verify the effectiveness of the feature pyramid, we conduct habilitation experiments based on different CNN such as VGG16, ResLite 50, and MobileLite V2. According to the result, ResLite 50 has the best and most stable performance among the three. Also, comparing the result with the baseline and the SPP-based models, all three CM architectures exhibit improved performance, confirming the effectiveness of the feature pyramid module. To objectively evaluate the performance on the proposed model, it is important to conduct a comparison with some state-of-art result. As a whole, the proposed method performs well on most of the evaluation metrics, and bold fonts represent some of them exceeding the latest research. So it is a promising and competitive model for the remote sensing image captioning task. I use visualization of attention to verify the model solves the multiscale problem. And I selected the images containing different sizes of airplanes within the same image and different variations of airplanes across the different images. In the heat map, regions with high attention are displayed in red and low attention in blue. When describing the airplane words, the LP-based method demonstrated remarkable performance by fully attending to aircraft regions of different sizes. Further, we conduct the visualization of attention for individual words in a sentence based on FP-based method. This is designed to observe how attention shifts when describing different objects. Through the images, we can see that attention changes dynamically when describing different words. Sentence diversity can be viewed as describing multiple perspectives of an image. And we get the best three sentences generated by the FP-based method. The blue fonts indicate the model can generate a sentence with diverse content and viewpoints. For example, in the last image, the model describes the river from its color and shape. For future plans, considering there are some errors in the generated sentence, we can improve from the model's accuracy in the next work. In the comparison experiments, the MobileLite V2 also performs well. On the other hand, the lightweight structure is a good option for generating captions on mobile devices. So this is a direction we intend to explore in future research. Here is a timetable of the main events. First, we reading the relevant papers and then conduct data collection and perform data preprocessing. And we train the model, adjust the model parameters, and perform the model evaluation and result analysis. And finally, we finish the report. Below is the reference list. That's all. Thank you for listening.